A major financial institution deployed a vector RAG system to assist internal auditors in querying regulatory compliance documents. The system had passed every benchmark. Retrieval accuracy looked clean. Latency was within SLA. Then, during a live audit review, the system returned a fabricated Basel III capital adequacy clause, one that did not exist in any source document. The auditors cited it in a formal report. Legal exposure followed. The incident was never publicly disclosed, but the pattern is documented across Fortune 500 deployments. Here is the critical detail. The system did not malfunction. It performed as designed. It retrieved the most semantically similar chunks and passed them to the LLM. But the query required reasoning across 3 separate regulatory documents, cross-referencing entities, dates, and jurisdictional conditions, and vector similarity has no mechanism for that. This was not a hallucination problem. This was not a prompt engineering problem. This was an architecture problem. And by the end of this lecture, you will have the exact framework to diagnose whether your current RAG system is one query away from the same failure. Let us be precise about what actually broke. Vector RAG operates on a single core assumption. Semantic proximity in embedding space equals informational relevance. For a large class of queries, factual lookups, document summarization, simple Q&A, that assumption holds. But consider a query like this. Under what conditions does Article 12 of Regulation A override the counterparty thresholds defined in Annex C of Regulation B, given the jurisdiction established in X's 2022 filing? That query requires a system to traverse a relationship graph. It must identify entity X, locate its 2020 filing, extract its jurisdiction, apply that jurisdiction as a conditional filter across 2 separate regulatory texts. Vector similarity cannot do this. It will retrieve chunks that are semantically close to individual fragments of the query, and those chunks in isolation look correct. The LLM then synthesizes a confident-sounding answer from incomplete, contextually disconnected evidence. This is what the ISO IHC AV quality model calls a functional correctness failure. The system produces an output, but that output does not accurately represent the intended behavior under all operating conditions. The gap is not in the model. The gap is in the retrieval architecture's inability to model relationships, and that grows exponentially as enterprise query complexity increases. But here is what most teams still do not realize. The fix is not better embeddings, it is a fundamentally different graph. Before we go deeper into the technical architecture, let me make a direct commitment about what this lecture delivers. After completing all 6 chapters, you will have concrete decision-making capabilities, not theoretical awareness, but actionable judgment. First, you will be able to classify any enterprise query by its structural complexity, whether it is a single hop lookup, a multi-hop relational traversal, or a dynamic multi-step reasoning task requiring external tool invocation. Second, you will be able to map that query class to the correct RAG tier, vector RAG, graph RAG, or agentic RAG, using explicit criteria, not intuition. Third, you will be able to justify that architectural choice using ISO IEC WEV synchronous quality attributes, specifically functional correctness, performance efficiency, and maintainability, which is exactly the language that architecture review boards and enterprise governance committees require. This is the gap that most RAG tutorials leave open. They show you how to build each system. They do not show you how to decide which system to build. That decision framework is what this lecture is about. And the reason it matters right now is that the cost of choosing the wrong RAG tier in production is no longer just a performance metric. As the financial audit showed us, it is a legal and governance exposure. But what does the decision tree actually look like? That is exactly are about to map. Now let us establish the mental model that will anchor everything in this lecture. Think of RAG not as a single technology, but as an evolutionary family of architectures, each tier solving a problem that the previous tier exposed in production. Vector RAG is the foundation, fast, scalable, effective for semantic search over flat document corpora. It breaks when queries require relational reasoning. Graph RAG is the second tier. It models entities and their relationships explicitly, enabling multi-hop traversal. It breaks when the reasoning path itself cannot be predetermined, when the system needs to decide, immediate execution, which data source to query next. Agentic RAG is the third tier. It embeds the retrieval process inside an autonomous reasoning loop, using tools, memory, and dynamic planning. Each tier is not a replacement for the previous one. It is a contextual upgrade triggered by a specific class of query complexity. Across this lecture, we will build a 3x3 decision matrix, query complexity on one axis, quality attribute priority on the other, that tells you precisely which tier to deploy. In Chapter 2, we begin with vector RAG. its internal architecture, its performance envelope, and the exact query patterns where it fails, so you can recognize those patterns in your own systems before they reach production. The question you should holding right now is this: which of your current RAG queries are actually relational and you just do not know it yet? Before we talk about where vector RAG breaks, we need to be precise about what it actually does, because most teams that adopt it never fully understood the pipeline they were running. The canonical vector RAG pipeline has 6 distinct stages. First, your source documents are split into chunks, fixed size or semantically bounded text segments. Second, each chunk is passed through an embedding model, producing a dense vector representation in a high-dimensional space, typically 7/16 to 1/5 and 5/536 dimensions. Third, those vectors are stored in a vector index, Pinecone, Weaviate, pgvector, whatever your stack uses. At query time, the user's question is embedded using the same model. The system then performs a top K similarity search against the index. The K most similar chunks are retrieved and injected into the LLM prompt as context. The LM generates an answer grounded in that retrieved context. That's the full loop. It's elegant, it's scalable, and it works until it doesn't. And the moment it stops working is precisely where this chapter begins. Vector RAG did not arrive fully formed. Between 2022 and 2024, the field went 3 recognizable generations at remarkable speed. In 22, we had naive RAG, a single pass retrieve, then read architecture. You embed, you retrieve, you generate, simple, brittle, and the dominant pattern in most early LangChain tutorials. By mid-2023, the research community identified systematic failure modes and responded with advanced RAG, adding pre-retrieval query rewriting, post-retrieval re-ranking, and hybrid sparse dense search. Papers like the 7 Failure Points Survey from the University of Melbourne formalized these gaps. Then in 24, modular RAG emerged, a composable, graph-like pipeline where retrieval, re-ranking, and generation modules can be orchestrated independently. The Gao et al. RAG survey taxonomy published in early 2024 codified this 3-tier model. But here's the critical insight. All 3 generations share the same fundamental substrate, vectors, and cosine similarity. The modules changed. The core mechanism did not. That unchanged core is exactly what imposes the ceiling we are about to examine. At the heart of every vector RAG system is a single mathematical operation: cosine similarity. Given a query vector and a set of document vectors, the system returns the chunks whose angular distance in embedding space is smallest. This is powerful because it captures semantic proximity. Automobile and car will score high similarity even with 0 lexical overlap. But here is the gap that practitioners rarely articulate. Cosine similarity maximizes semantic closeness, not relational correctness. If the answer to your query requires traversing a relationship, what regulation governs the subsidiary that signed this contract? The embedding of that question may be semantically close to many chunks, none of which contain the connected answer. The vector space has no edges, no links, no graph. It is a flat field of points. And in that flatness lies the structural ceiling of the entire paradigm. This is not a bug that better embeddings will fix. It is a geometric property of the representation itself. So ask yourself, how many of your enterprise queries actually fit inside flat field? Let me make this concrete with a scenario that enterprise legal and compliance teams encounter every week. Single hop query. What is the governing law clause in contract A? Vector handles us. The query embeds close to the chunk containing that clause. Top 1 retrieval delivers the answer. Accuracy is high. Now introduce a multi-hop relational query. Regulatory framework applies to the subsidiary entity named in the indemnification clause of contract A, given the jurisdiction established in the Master Services Agreement. This query requires 3 traversals. Locate the indemnification clause, identify the subsidiary entity, cross-reference that entity's jurisdiction against the MSA, then map to applicable regulation. Vector RAG will retrieve chunks that are semantically similar to the query, likely the indemnification clause itself and some regulatory boilerplate. But the relational chain connecting those facts is never assembled. The LLM receives fragments. It either hallucinates a plausible-sounding answer or correctly admits it cannot determine the answer. In enterprise production, the first outcome is catastrophic and the second is unacceptable. This is not an edge case. Multi-hop relational queries represent the majority of high-value enterprise knowledge work. Beyond multi-hop failures, vector RAG has 3 hard structural ceilings that no amount of prompt engineering or model scaling will eliminate. First, chunk boundary artifacts. When a document is split, critical information is routinely bisected. A contract clause, a financial table, a regulatory definition. All can be severed at an arbitrary boundary. The retriever may surface half the information, and the LLM will complete the gap with plausible hallucination. Second, The lost-in-the-middle degradation effect. Research by Liu et al. In 2023 demonstrated empirically that, said LLM, underweight information placed in the middle of a long context window. If you retrieve 10 chunks and the critical answer is in chunks 4 through 6, the LLM's attention mechanism will systematically underweight it. This is not a retrieval problem, it is a generation problem triggered by retrieval design. Third and most fundamental, the complete absence of structured relationship encoding. There is no mechanism in a vector index to represent that document A cites document B, that entity X governs entity Y, or that rule 1 supersedes rule 2. These structural facts are either buried in text and retrievable only by chance, or they are simply lost. These three ceilings are additive. They compound in complex, enterprise corpora. To ground this in a framework that enterprise architects and technical exam boards both recognize, let us map vector RAG's structural weaknesses directly to IEC UMISMI sync software quality attributes. Under functional correctness, vector RAG achieves acceptable accuracy on simple factual retrieval, but scores poorly on multi-hop queries. Correctness degrades nonlinearly as query complexity increases. Under traceability, a subattribute of maintainability, there is no native provenance chain in a vector retrieval result. You can record which chunks were retrieved, but you cannot reconstruct why those chunks satisfy the query's relational requirements. Under maintainability itself, as the corpus grows and documents are updated, re-indexing is full corpus by default. Incremental graph updates, which GraphRag enables, are not available. Under performance efficiency, vector genuinely strong here. Sub 100 milliseconds top EK retrieval at scale is achievable. This is a real advantage. The quality model tells us something important. Vector RAG is not universally weak. It is selectively weak in exactly the attributes that matter most for complex enterprise knowledge systems. That selective weakness is what the next chapter's architecture directly addresses. Having established where vector RAG breaks, let me be equally precise about where it remains the optimal architecture, because as over-engineering is as costly as under-engineering. Vector RAG is the correct choice when all of the following conditions hold simultaneously. First, query relational depth is 1. The answer exists within a single document chunk, with no cross-document traversal required. Second, query volume is high. You are serving thousands to tens of thousands of requests per day, where GraphRag's higher per-query latency would be unacceptable. Third, the domain is relatively static. Your corpus is not a densely interconnected knowledge graph, but a collection of largely independent documents. Think product FAQ systems, internal policy lookup, customer support knowledge bases, and document semantic search endpoints. Fourth, the answer surface is bounded. Users are not asking investigative or analytical questions, they are looking up known facts. Fifth, latency SAR strict. Sub 200 milliseconds response time requirements effectively eliminate GraphRag and Agentic RAG from contention. If all 5 conditions are met, adding GraphRag complexity is pure cost with no benefit. The discipline of not over-architecting is itself a professional competency. We now have everything we need. Draw the decision boundary cleanly. The primary axis for choosing your RAG architecture is not data volume. It is not model size. It is not even accuracy requirements in isolation. The primary axis is the complexity of reasoning to answer your target query class. On the left side of that axis, single hop, fact lookup queries. Vector RAG is optimal, fast, scalable, cheap, sufficient. As you move right along the complexity axis toward multi-hop relational reasoning, temporal sequencing, hierarchical entity traversal, and causal chain analysis, vector RAG's ISO synchronous correctness score declines steeply while its operating cost advantage erodes against the cost of downstream hallucination remediation. The inflection point, the GraphRag threshold, is reached when your 50 query requires or more relational hops across structured entities. That is the signal to upgrade the substrate. In the next chapter, we will examine exactly how GraphRag encodes relationships as first-class data, not as text to be semantically approximated, but as explicit edges in a traversable knowledge graph. The architecture shift is more profound than it appears, and the enterprise implications are significant. Stay with us. In the previous chapter, we exposed the core failure mode of vector RAG. It treats every document as an isolated island of meaning. Cosine similarity cannot tell you that the CFO who approved the merger and the executive who signed the deal are the same person. Because semantic proximity is not the same as structured knowledge, GraphRag makes a fundamentally different architectural bet. Instead of encoding text as floating-point vectors in a flat index, it extracts entities, classifies them by type, and explicitly records the typed relationships between them as first-class data. The result is a knowledge graph, a property graph stored in a system like Neo4j. where every node is a named entity and every AILD relationship triple. Subject, 보다 큰 predicate, 보다 큰 object. The critical insight here is that graph structure is information that dense embeddings silently discard. A vector index knows that acquisition and merger are similar concepts. A knowledge graph knows that Acme Corp acquired Target Corp on a specific date for a specific price, approved by a specific board. That is a qualitative difference in representational power, and it changes everything about what queries you can answer reliably. But encoding relationships as first-class data comes with a price. Let's see exactly what that pipeline looks like. Microsoft's GraphRag paper, released in 2024, is influential production-grade blueprint for GraphRag architecture, and it introduces two ideas that fundamentally change how we think about retrieval at scale. The first idea is community detection. After extracting entities and relationships from all documents, Microsoft applies the Leiden algorithm, a hierarchical graph clustering algorithm, to partition the knowledge graph into semantically coherent communities. Think of it as automatically discovering that nodes about Basel-Torfer, capital adequacy ratio, and Tier 1 capital all belong to a banking regulation community without any human labeling. The second idea is hierarchical summarization. For each detected community, an LLM generates a community summary, a dense natural language synthesis of everything that community represents. These summaries become the retrieval targets for global queries. Broad analytical questions like what are the major regulatory risks facing European banks that no single document chunk can answer. Local queries, specific factual lookups, still route to the direct entity and relationship retrieval. This dual routing architecture is the key engineering insight. Not every question has the same retrieval shape. But there is a hidden cost in this elegance. The Leiden clustering and hierarchical summarization must be rerun whenever the graph changes significantly. We will quantify that cost in Section 2. Let's make this concrete with a query that would completely break a vector index. Suppose a compliance analyst asks, which executives at firms that receive enforcement actions in 2023 also served on the audit committees of companies audited by the same Big Four firm? This is a four-hop traverse of 보다 큰 serves on, 보다 큰 audit committee, 보다 큰 belongs to, 보다 큰 company, 보다 큰 audited by, 큰 audit firm, then cross-referenced back to SE enforcement actions linked to affiliated firms. A vector index would return semantically similar chunks about SEC enforcement and audit committees. But it cannot resolve the structural path. In Cypher, this query is expressed as a clean pattern match. Matchy path from executive through serves on to audit committee, through belongs to company, through audited by to audit firm, then back-referencing enforcement actions on related entities. With a Boer filter on year equals 2023. The graph traversal engine resolves this in milliseconds once the graph exists. The key phrase there is once the graph exists. Building this graph is where the real architectural work lies. This is precisely where GraphRag's cost profile diverges sharply from vector RAG, and that divergence is what we analyze next. Let's talk honestly about what it costs to build a production knowledge graph, because this is where many GraphRag proofs of concept collapse before reaching production. The ingestion pipeline has four mandatory stages. First, named entity recognition, NER, identifies and classifies entities in text. Second, entity linking resolves that Goldman Sachs, Goldman, and GS in different documents all refer to the same node. Third, coreference resolution determines that the bank and the firm in a paragraph all refer to the same previously mentioned entity. Fourth, relationship extraction identifies and labels the semantic relationships between resolved entities. Each of these stages introduces latency and error accumulation. Based on enterprise deployments documented in the literature, GraphRag ingestion pipelines typically run 8 to 15 times slower than equivalent vector embedding pipelines on the same document corpus. For a 10 million token document set, vector ingestion completes in approximately 2 hours. Graph construction with full NAR and relationship extraction requires 16 to 30 hours on comparable compute. The critical architectural implication: GraphRag is not a drop-in replacement for vector RAG. It is a different operational commitment. The question is whether the query accuracy gains justify that commitment for your specific use case. And that question leads us directly to the hybrid architecture debate. Given the ingestion cost of pure GraphRag, the most pragmatic enterprise pattern is the hybrid graph plus vector architecture. The intuition is straightforward. Not all retrieval is structural. Some queries are genuinely semantic. Find documents about supply chain resilience strategies, where dense vector retrieval is optimal. Other queries are structurally relational, which suppliers are connected to both our Tier 1 vendors and flagged regulatory entities, where graph traversal is essential. The hybrid architecture uses a query classifier, a router, to determine retrieval strategy per query, then fuses results from both retrieval paths into a unified context window. The fusion layer is where the engineering judgment lies. Do you concatenate results with source annotations, or do you use a cross-encoder hierarchy to score relevance across both result sets before passing to the generator? Production evidence from deployments at financial services firms shows that hybrid architectures outperform pure graph RAG on mixed query portfolios by 12 to 18% on answer accuracy benchmarks, while reducing average query latency compared to always running full graph traversal. But pure graph RAG still dominates on structured multi-hop queries by a significant margin. The architectural lesson. The retrieval strategy should match the query topology, and match requires a routing layer, which itself introduces a new failure mode. We will revisit routing failure when we reach Agentic RAG. Before you can build a knowledge graph, you need a graph schema, and schema design is where domain expertise becomes a hard technical requirement, not a nice-to-have. In financial services, your entity taxonomy must encode the regulatory and organizational hierarchy. Entities, beneficial ownership chains, instrument types, counterparty relationships, and regulatory classifications under frameworks like LEI, the Legal Entity Identifier Standard. Get the schema wrong, and your graph will produce structurally valid, but semantically meaningless traversals. In legal document intelligence, the ontology must capture clause types, obligation relationships, condition precedent structures, and cross-reference chains between contract sections and regulatory statutes. The schema is not a database design exercise. It is a domain modeling exercise that requires subject matter expert validation. Two critical design decisions recur across enterprise domains. First, how granular should relationship types be? Coarse relationships like related to are easy to extract but useless for traversal. Fine-grained relationships like guarantees, obligation of are highly valuable but require more sophisticated extraction models. Second, how do you handle schema evolution when the domain model changes? In a vector index, adding a new document type is trivially cheap. In a knowledge graph, it may require remodeling existing nodes and rerunning extraction across the entire corpus. This is the modifiability cost that ISO IAC will help us quantify in our final section. Let's be rigorous about the three production costs of graph RAG that rarely appear in benchmark papers. The first cost is ingestion latency. We quantified this earlier, 8 to 15 times slower than vector pipelines. But the operational impact is more significant than the raw number suggests. If your enterprise knowledge base receives continuous document updates, regulatory filings, contract amendments, news events, the graph must be incrementally updated. Incremental graph updates require conflict resolution for entity merging, which creates write contention in the graph database under high ingestion throughput. The second cost is schema maintenance burden. Every time your document domain evolves, new product categories, new regulatory frameworks, new organizational structures, your graph schema may need to change. Schema changes in a property graph cascade through existing nodes and relationships, potentially invalidating previously valid traversal paths. This is a modifiability liability that has no equivalent in a vector index. The third cost is query planning complexity. Cipher or SPARQL queries for multi-hop traversals require expert authorship or a reliable text-to-cipher translation layer. Text-to-cipher via LLM achieves approximately 660 to 75% accuracy on complex multi-hop queries in current benchmarks, meaning roughly 1 in 3 complex queries will produce an incorrect or incomplete graph traversal. These three costs form a triangle of operational complexity that must be weighed against the accuracy gains. The question an enterprise architect must answer is, does my query portfolio justify this operational surface area? The ISO quality framework in the next scene gives us the vocabulary to answer that question precisely. Let's close this chapter with the architectural decision framework you actually need. ISO IAC finds 8 software quality characteristics. A map graph RAG against them reveals exactly where it wins, where it loses, and critically, which characteristics are non-negotiable for your specific enterprise context. Graph RAG delivers significant gains on 2 ISO IAC characteristics. Degree to which the system provides correct results, and traceability, captured under accountability in the security characteristics. When a graph RAG system answers a compliance query, every fact in the response is traceable to a specific entity node, a specific relationship edge, and a specific source document. That auditability is not a nice-to-have in regulated industries, it is a regulatory requirement. However, graph RAG takes measurable hits on 2 other characteristics: performance efficiency, specifically response time behavior under complex traversal queries, and maintainability, specifically modifiability, which we quantified through schema evolution costs. The enterprise fit decision reduces to this. If your workload is dominated by multi-hop relational queries where incorrect answers carry regulatory or financial consequence, and if your domain schema is relatively stable, Graph RAG's attribute profile is the right fit. If your workload is predominantly semantic, your schema evolves rapidly, or your team lacks graph database operational expertise, the quality attribute costs outweigh the benefits. And if your queries are neither purely semantic nor purely structural, but require dynamic reasoning about which retrieval strategy to use, then neither vector RAG nor graph RAG is sufficient. That is precisely the gap that Agentic RAG was designed to fill, and it is where our next chapter begins. In the previous chapter, we saw how graph RAG encodes relationships as first-class data, a major step beyond flat vector retrieval. But here is a harder question. What happens when no single retrieval strategy is sufficient for the query at hand? What happens when the system itself needs to decide, at runtime, whether to use a vector index, a knowledge graph, a SQL database, or an external API? This is the fundamental problem that Agentic RAG was designed to solve. Agentic RAG is not a retrieval method. It is an architectural shift. Instead of a static pipeline where retrieval is hard-coded before inference, an LLM-orchestrated agent sits at the center and dynamically selects which retrieval tool to invoke, when to invoke it, and how many times. The ISO-IAC-YV-Sync-with-These quality attribute of adaptability is precisely what this architecture maximizes. The system adapts its own retrieval strategy to the complexity of each unique query. Think of it this way. Traditional RAG is a fixed assembly line. Agentic RAG is a skilled engineer who reads the blueprint, chooses the right tools from the workshop, and iterates until the out meets specification. But this power comes with costs that will break your production system if you are not prepared, and we will get to those costs shortly. The engine that powers Agentic RAG is the React pattern, reason, then act. Originally published by Yao et al. At Princeton in 2022, React showed that interleaving reasoning traces with action calls to external tools dramatically outperforms either reasoning alone or retrieval alone. Here is how the loop operates in an enterprise context. Step 1. The agent receives the user query and generates an explicit reasoning trace. It plans which information gaps need to be filled. Step 2. Based on that reasoning, it selects a tool. This could be a vector similarity search for semantic lookup, a graph traversal for relationship queries, a SQL execution for structured aggregation, or a REST API call for real-time data. Step 3. The tool returns an observation, a chunk of retrieved evidence. Step 4. The agent integrates that observation into its reasoning context and reevaluates. Is the answer now sufficient? If yes, generate the final response. If no, plan the next retrieval action. This is not a pipeline, this is a feedback-driven control loop. And here is the critical insight for enterprise architects. The quality of tool descriptions in your system prompt directly determines the agent's tool selection accuracy. Garbage tool metadata produces garbage retrieval decisions. But wait, what happens when one query requires not one tool call but 5, running in parallel across different data domains? Let us make this concrete with a real enterprise scenario. Imagine a query from a financial analyst. Why did our Q3 revenue decline in the APAC region? And which product lines were most affected? This is a multidimensional question. No single retrieval source can answer it. Watch how an agentic RAG system decomposes this. The central query branches into at least 4 parallel sub-questions. First, what were the Q3 APAC revenue figures? This routes to a SQL database for structured financial aggregation. Second, what external market conditions affected APAC in Q3? This routes to a vector index over news and analyst reports. Third, which product lines have APAC as a primary market? This routes to a knowledge graph traversal of product region relationships. Fourth, were there any operational disruptions in the supply chain? This routes to an internal incident management API. All 4 subqueries execute, ideally in parallel, and their results are synthesized by the agent into a coherent causal explanation. This is the power of heterogeneous retrieval orchestration. But here is the uncomfortable truth. This decomposition only works correctly if your agent has been given well-defined tool boundaries and your retrieval sources are maintained with consistent data quality. In the next section, we will see how GRAG and RAG converge into an architecture that is greater than the sum of its parts. We have examined Agentic RAG and Graph RAG as separate architectures. Now we need to talk about what happens when you combine them. Because the convergence architecture is where the most advanced enterprise AI systems are being built today. Agentic Graph RAG is the integration of graph-structured retrieval with agent-driven orchestration. Here is why this combination is uniquely powerful. Graph RAG gives the system the ability to traverse relationships, to follow edges from entity to entity and surface non-obvious connections. Agentic orchestration gives the system the ability to decide dynamically which traversal paths to explore based on intermediate findings. In isolation, graph traversal requires you to predefine a traversal depth and starting nodes. In isolation, an agent without graph access falls back to vector similarity for relational queries. Together, the agent can start a traversal at one node, observe the intermediate results, and then dynamically decide to extend the traversal in a new direction, switch to a vector search for semantic enrichment, or invoke a SQL tool for quantitative validation, all within a single query lifecycle. Think of the architecture as a layered stack. At the bottom, your data layer, knowledge graphs, vector indexes, relational databases. Above that, your tool layer, graph query executors, embedding search engines, SQL interfaces. Above that, your agent orchestration layer, the React loop with memory and planning. And at the top, your application layer, the interface that receives the final synthesized response. Each layer must be independently scalable, and the boundaries between them must be clean. Vague boundaries are where enterprise AI systems go to die. Two frameworks dominate the Agentic Graph RAG implementation space in 2024 and 2025. From LangChain and LlamaIndex with its agent and graph integration modules. Understanding their architectural differences matters enormously when you are making an enterprise framework decision, because switching frameworks mid-project is catastrophically expensive. LangGraph models agent behavior as a stateful directed graph of nodes and edges. Each node is a Python function, a retrieval step, a reasoning step, or a synthesis step. Is defining conditional routing logic. CredNgraph exposes graph traversal as a native node type, meaning your knowledge graph query is a first-class citizen in the agent workflow graph itself. The mental model is, your agent is a graph, and it reasons over a graph. This architectural elegance comes with steeper learning curve and more explicit state management overhead. LlamaIndex takes a different approach. It provides a higher-level abstraction through its query engine and agent runner interfaces. Graph traversal is exposed as a knowledge graph query tool, a plugin tool that the agent can select like any other retrieval tool. This makes it faster to prototype and easier to swap components, but the lower-level control that LangGraph offers is abstracted away. For enterprise architects, the decision criterion is this. If your agent workflow has complex conditional branching and stateful multi-turn interactions, choose LangGraph. If you need rapid prototyping with modular component swapping, choose LlamaIndex. Both are valid. Neither is universally superior. And here is the question you must answer before choosing either. How deterministic does your agent behavior need to be in production? As query complexity grows beyond what a single agent can reliably handle, enterprise architectures evolve toward multi-agent decomposition. And this is where Agentic Graph RAG reaches its most sophisticated form. The pattern works as follows. A coordinator agent receives the user query and performs high-level planning. It identifies which retrieval domains are relevant and dispatches subtasks to specialist retrieval agents. The graph retrieval agent is responsible exclusively for knowledge graph traversal. It understands the graph schema, selects appropriate Cypher or Spark YOL queries, and returns structured relationship evidence. The vector retrieval agent handles semantic similarity search. It manages embedding model selection, chunk retrieval, and relevance scoring. The SQL retrieval agent handles structured data queries. It generates and SQL manages schema context and returns tabular results. Finally, a synthesis agent receives all specialist outputs and assembles the final coherent response, resolving any contradictions between sources. This is not science fiction. Microsoft's Autogen framework, Amazon Bedrock multi-agent collaboration, and Vertex AI Agent Builder, all variants of this pattern in production today. The coordinator specialist pattern maps directly to the ISO/ISC ROIS inclusive modularity attribute. Each specialist agent is independently testable, replaceable. But here is the critical warning. The coordinator agent is a single point of failure. If its planning logic is flawed, every downstream retrieval is wasted computation. Next, we confront the production costs of running this architecture at enterprise scale, and some of the numbers will surprise you. We have spent 2 sections describing the power of Agentic RAG. Now we need to talk honestly about why it breaks in production. Because the failure modes are severe, they are predictable, and they are frequently underestimated in pre-production evaluations. There are 4 production risks that every enterprise architect must internalize before deploying Agentic RAG at scale. First, latency unpredictability. A traditional pipeline has a deterministic latency profile. You can bound it. An Agentic RAG system does not. Each additional tool call adds network latency, LLM inference time, and context window processing overhead. A query that requires 5 sequential tool calls can easily take 15 to 30 seconds, unacceptable for interactive user interfaces. Second, compounding costs. Every reasoning trace, every tool call result, every observation is appended to the context window. In a 5-hop retrieval chain, you may be processing 10,000 tokens for what appears to be a simple question. At scale, this creates budget overruns that were not modeled in your initial cost projections. Third, non-deterministic behavior. The same query submitted twice may follow different retrieval paths, invoke different tools in different orders, and produce subtly different answers. This violates the auditability requirements of regulated industries, finance, healthcare. Fourth, runaway loops. With explicit termination guards, an agent that cannot find a satisfactory answer will continue calling tools indefinitely. I have seen production systems burn through 30 tool calls and $500 of API credits on a single malformed query. The architecture gives you power, but power without guardrails is just a liability. The good news is that all 4 production risks are mitigatable, but only if you implement guardrails before you deploy, not after your first production incident. Here is the minimum viable guardrail set that every enterprise agentic RAG system must have before it touches production traffic. Tool timeout limits. Every tool call must have a hard timeout, typically 2 to 5 seconds for internal retrieval, 10 seconds for external APIs. If a tool exceeds its timeout, the agent must receive a stirrer observation and plan around the missing data, not hang indefinitely. Maximum iteration caps. Set a hard ceiling on the number of React loop iterations, typically 3 to 7, depending on query complexity class. When the cap is reached, the agent must return its best available answer with an explicit uncertainty flag. Structured output validation. Agent responses must be validated against a schema before delivery to the application layer. Unstructured or malformed outputs from runaway agents must be caught at this layer, not surfaced to users. And critically, distributed trace observability. Every agent decision, every tool call, every observation must be logged with a trace ID and correlation context. Without this, you cannot debug non-deterministic failures in production. Tools like Langsmith, RI's Phoenix, and OpenTelemetry-compatible tracing backends are not optional extras. They are foundational infrastructure for production agentic RAG. Remember, you cannot improve what you cannot observe. This chapter has shown you the full power and the full cost of agentic RAG. In the next chapter, we will build the decision framework that tells you precisely when agentic RAG is justified, and when simpler alternatives will serve you better with a fraction of the operational complexity. Most RAG failures in production are not engineering failures. They are selection failures. Teams pick an architecture before they understand the problem shape. So let us fix that right now with a concrete decision model. We evaluate every RAG deployment along 3 axes. Axis 1, query relational depth. How many entity relationships must be traversed to answer the question? Axis 2, data structure type. Is your corpus flat documents, semi-structured records, or a native knowledge graph? Axis 3, response latency budget. Does your SLA demand sub-second answers, or can reasoning take 3 to 10 seconds? These 3 axes are not arbitrary. They map directly to ISO IESC with any single D's quality attributes: accuracy, time behavior, and maintainability. When you score each axis, you get a coordinate in 3-dimensional architecture space, and that coordinate tells you which RAG tier to deploy. But here's the critical insight most architects miss: these axes interact. A low latency requirement can eliminate graph RAG entirely, even when relational depth is high. How do we resolve that conflict? The decision matrix in the next scene gives you the exact rules. Now let us make this operational. The decision matrix takes every combination of the 3 axes and maps it to a RAG tier with explicit boundary conditions. In the vector RAG zone, relational depth is 1 to 2 hops, data is flat or chunked documents, and latency budget is under 1 second. This is your enterprise search, FAQ bot, and document summarization territory. In the graph RAG zone, relational depth climbs to 3 to 5 hops, data has native entity relationships. Think regulatory clauses, product catalogs dependencies, or clinical ontologies, and latency budget allows 1 to 4 seconds. In the agentic RAG zone, relational depth exceeds 5 hops or is unknown at query time, the data schema is heterogeneous across multiple sources, and latency budget is 3 to 10 seconds or user-initiated batch. Now here is where architects make mistakes: the overlap zones. When relational depth is medium but latency is tight, you do not upgrade to graph RAG. You optimize vector RAG with metadata filtering. When relational depth is high but data is unstructured, you do not downgrade to vector RAG. You build a lightweight extraction graph on top. The boundary conditions are as important as the zones themselves. And in the next scene, I will give you a single proxy metric you can calculate in 15 minutes to score Axis 1 without building anything. Axis 1, query relational depth, is the most impactful axis, but it is also the hardest to score before you have a running system. So here is a practical proxy metric you can use in a field assessment today: expected graph hop count, or EGHC. The method is simple. Take a sample of 20 to 30 representative queries from your target use case. For each query, manually identify the minimum number of distinct entity transitions required to answer it correctly. A query like what is our refund policy? Scores 1, single entity, single document. A query like which Basel III capital requirements apply to our cross-border derivative positions held in the Singapore subsidiary? Scores 4 to 5. Regulation entity instrument type, jurisdiction, subsidiary structure, capital rule. Average the scores across your sample. An average EGHC below 2 points to vector RAG. 2 to 4 points to graph RAG. Above 4, or with high variance indicating unpredictable depth, points to Agentic RAG. This is not a perfect metric, but it is a 15-minute field tool that prevents 6-month architecture regrets. Now, this model works in theory. But does it hold under the pressures of real enterprise domains like finance, legal, and healthcare? The next section will stress test every assumption we just made. Let us now apply the decision framework to financial compliance, one of the highest stakes RAG deployment environments in the enterprise. Financial compliance queries are structurally complex. A question like, does our trading book exposure in Tier 2 capital instruments comply with Basel III Article 92 given our current leverage ratio, requires traversing at minimum 5 entity relationships. The trading book entity, the capital instrument classification, the regulatory article reference, the leverage ratio calculation rule, and the jurisdiction-specific implementation of Basel III into local regulation. That EGHC score of 5+ places this squarely in graph RAG territory. But here is where finance departs from the pure architecture model. Audit trail requirements. Regulators, whether the ECB, the FCA, or the SEC, require that every compliance determination be traceable to specific source document, version, and retrieval. DAMP. Graph RAG alone does not natively produce this audit trail. This is the trigger condition for adding agentic orchestration on top of graph RAG, not to handle depth, but to enforce provenance logging at every retrieval step. The comparison between standard vector RAG and this agentic augmented graph RAG pattern reveals a critical governance gap that most AI teams discover only after a compliance audit. Do not be that team. The legal domain, which we examine next, introduces an equally demanding but structurally different challenge. Legal AI is the domain where the decision matrix gets most stress tested, because legal documents have 2 fundamentally different query patterns that require 2 different RAG tiers, and most legal AI deployments conflate them. The first pattern is contract clause dependency analysis. When a lawyer asks, does clause 14.3 of this agreement conflict with the indemnification scope defined in clause 8.1 and the liability cap in clause 22.7? This is an intra-document graph problem. The entities are clauses, the edges are semantic dependencies, and the hop count is 3 to 4. Graph RAG with a document internal ontology is the correct architecture. Build a clause dependency graph per contract, traverse it with graph RAG, and you outperform any vector similarity approach by a significant margin on conf detection accuracy. The second pattern is precedent chain retrieval. When a lawyer asks which prior court decisions establish the enforceability of this specific limitation of liability clause under New York commercial law, and how did each decision modify the interpretation? This is a multi-document, multi-hop, temporally ordered traversal. The precedent chain is a directed acyclic graph across thousands of cases. The query depth is unpredictable. This requires agentic graph RAG with a legal knowledge graph backend. Conflating these 2 patterns, using simple vector RAG for both, is the single most common failure mode in legal AI deployments today. And the cost is not just accuracy, it is professional liability for the law firm. Healthcare adds yet another dimension that neither finance nor legal faces in the same way. Watch what changes. Healthcare RAG operates under constraints that do not exist in finance or legal. The intersection of clinical complexity and PHI, protected health information, compliance under HIPAA in the United States, and equivalent frameworks globally. Let us separate the architectural need from the compliance constraint. Because they pull in opposite directions, the architectural need is clear. Clinical pathway reasoning and drug interaction analysis are high EGHC problems. A query like, given this patient's comorbidities, type 2 diabetes, stage 3 CKD, and hypertension, what are the contraindicated medications across all 3 conditions, and which approved treatment pathway minimizes interaction risk? Requires traversing a drug interaction graph, a clinical conjugation ontology, and a treatment protocol graph simultaneously. EDHC score is 5 to 7. Agentic RAG is architecturally correct. But here is the compliance constraint that overrides architecture. Any RAG system that processes PHI, including clinical notes, diagnosis, and prescription RAG records, cannot route that data through cloud-hosted LLM API unless the cloud provider holds a signed business associate agreement and the data governance policy explicitly permits it. This eliminates most public cloud agentic RAG deployments for direct patient data. The practical resolution is a hybrid architecture, an on-premises or private cloud graph traversal layer that de-identifies data before any external LLM inference call. This is not a performance trade-off, it is a legal boundary. The compliance and governance overlay we cover next will formalize exactly these kinds of overrides. We have now seen 3 domains where compliance constraints alter or override the pure architectural recommendation from the decision matrix. This is not an edge case. It is the norm in enterprise AI. So the decision framework must include a compliance overlay layer that is evaluated before you finalize any RAG tier selection. There are 4 compliance constraint categories that matter most in 2024 and beyond. First, data residency. GDPR Article 46, China's PPL. India's DPDP Act all impose data localization requirements that can prohibit any cloud-based component from processing certain data categories. If your data must stay in country, your agentic RAG options shrink to self-hosted models only. Second, explainability mandates. The EU AI Act's requirements for high-risk AI systems, which include many financial and healthcare AI applications, demand that the system be able to explain how it reached a conclusion. Vector RAG's black box similarity scoring fails this test by default. Graph RAG's explicit traversal path is inherently more explainable. Third, model governance. Enterprises subject to SOC 2, ISO 1, or sector-specific frameworks must document which models are used, when they were updated, and what their known failure modes are. This governance burden increases significantly with agentic RAG due to the non-deterministic agent decision paths. Fourth, audit logging. Every retrieval event in a regulated enterprise RAG system must generate an immutable log entry. This is a mandatory architectural component, not optional. The next scene defines the minimum governance architecture that satisfies these requirements across all 3 RAG tiers. With the compliance constraints cataloged, we can now define the minimum governance architecture that every enterprise RAG system must implement, regardless of which tier it uses. Think of this as the governance wrapper that sits around your RAG tier, not inside it. 3 components are non-negotiable. Component 1, Retrieval Audit Log. Every retrieval event must generate a structured log entry containing the query hash, the retrieved source identifiers, their version timestamps, the retrieval score or traversal path, and the model version that processed the result. This log must be write once and tamper evident. In practice, this means your logging pipeline goes to an append-only store, not a mutable database. Component 2, Source Attribution in Responses. Every answer generated by the RAG system must include inline citations that are machine-readable, not just human-readable prose. The citation must include document ID, section or node reference, and confidence score. This is what allows downstream compliance systems to verify the answer against the source. Component 3, Human-in-the-loop Escalation. Define a confidence threshold. Typically a retrieval score below 0.7 or a graph traversal that returns fewer than 2 corroborating sources. When the system falls below this threshold, it must not return a direct answer. It must route to a human reviewer queue. These 3 components are not features, they are architectural requirements for any enterprise RAG that touches regulated data. And with this governance overlay in place, you now have the complete decision framework. In the final chapter, we will synthesize everything and answer the original question. Is RAG dead, or has it evolved into something more powerful and more demanding than anyone anticipated? Let's bring everything together with a final, definitive comparison. Across this entire lecture, we have evaluated 3 RAG tiers: Vector RAG, Graph RAG, and RAG. And now we score each one against the IEC quality attribute model. On correctness, Vector RAG scores moderate. It retrieves semantically similar chunks but cannot reason across relational boundaries. Graph RAG scores high on correctness precisely because it traverses entity relationships, eliminating the hallucination paths caused by disconnected context. Agentic RAG scores highest, but with an asterisk, correctness is contingent on orchestration quality. On performance efficiency, Vector RAG wins. Sub 100 milliseconds retrieval at scale is achievable with HNSW indexing. Graph RAG introduces graph traversal overhead, typically 300 milliseconds to 2 seconds depending on hop depth. Agentic RAG can balloon to 10 or even 30 seconds when multi-tool chains are invoked. On maintainability, the story reverses. Vector RAG becomes a maintenance liability as your corpus grows, embedding drift, chunk boundary rot, index versioning all compound. Graph RAG's ontology requires governed schema evolution, but rewards that discipline with traceable reasoning paths. Agentic RAG demands the highest operational maturity. Agent prompt versioning, tool contract management, and circuit breaker policies are non-negotiable. And on traceability, the attribute most enterprise compliance teams demand, Vector RAG is the weakest. You can log which chunks were retrieved, but you cannot explain the model chose to ignore others. Graph RAG gives you a traversal path you can audit. Agentic RAG gives you a full execution trace, if you instrument it correctly. The conclusion is not that one architecture wins. The conclusion is that each architecture solves a different quality problem. Choosing the wrong tier is not a technical mistake, it is an architectural misdiagnosis. And that distinction is exactly what separates a production AI system from a prototype that breaks under enterprise load. Now let's make this actionable. The architecture evolution is not a one-time migration decision. It is a progressive adoption journey governed by measurable thresholds. You start with Vector RAG. It is the right baseline for every organization. Fast to deploy, low operational overhead, and sufficient for the majority of single-document, single-hop query workloads. But you do not stop there. From day one, you instrument your system for query complexity signals. Track the ratio of multi-entity queries to total queries, measure retrieval confidence score distributions, and log user reformulation rates. Those are leading indicators that your Vector RAG ceiling is approaching. When your relational depth threshold exceeds roughly 30% of production queries involving 2 or more entity hops, that is your migration trigger to Graph RAG. You build a knowledge graph layer on top of your existing vector store. You do not replace it, you augment it. Then, as your use cases evolve toward cross-system reasoning, when users are asking questions that require synthesizing data from your CRM, your ERP, and your document corpus simultaneously, that is when Agentic RAG orchestration becomes justified. The critical insight here is that each transition is data-driven, not opinion-driven. You are not upgrading because Graph RAG is newer. You are upgrading because your query telemetry has crossed a threshold that the previous tier cannot serve within your SLA. This is what separates an enterprise AI architect from a developer who chases framework releases. The migration path is not a ladder you climb once. And in the next section, we will give you the reference card that makes every future decision faster. Let's consolidate everything into a single reference card, the one you will return to when you are sitting in an architecture to review and someone asks, which RAG do we use? The 3-axis decision model is your first tool. Axis 1, query relational depth. If your queries are single hop, Vector RAG is sufficient. If they are multi-hop entity traversals, Graph RAG is required. If they demand dynamic tool invocation across heterogeneous systems, Agentic RAG is your answer. Axis 2, latency tolerance. Real-time user-facing applications demand Vector RAG's sub-100 millisecond profile. Internal analyst workflows can tolerate Graph RAG's 3 milliseconds to 2-second range. Batch intelligence and autonomous process automation can absorb Agentic RAG's multi-second execution windows. Axis 3, governance maturity. Be honest about where your organization sits. If you do not have an MLOps pipeline, an Agentic RAG deployment will create more risk than value. Now for the 5 non-negotiable governance requirements that apply regardless of which tier you choose. First, retrieval provenance logging. Every context chunk or graph path must be logged with source metadata. Second, hallucination rate SLA. Define an acceptable threshold before you deploy, not after an incident. Third, embedding or ontology versioning. Your knowledge representation is a schema. Treat it with the same discipline as a database migration. Fourth, latency budget per query class. Set it in your SLO and enforce it with circuit breakers. Fifth, access control propagation. Your RAG system must inherit the same-day access permissions as the source systems it retrieves from. These 5 requirements are not optional enhancements. They are the minimum viable governance layer for any enterprise RAG system operating under regulatory or fiduciary obligation. You now have everything you need to make the decision confidently. But knowing the decision framework is only half the battle. The other half is knowing what comes next. RAG is not dead, but it has evolved into something that demands architectural decision-making, not just engineering implementation. The journey from Vector RAG to Graph RAG to Agentic RAG is not a story of obsolescence. It is a story of scope expansion. Each tier exists because a class of enterprise problems genuinely requires it. Your job as an AI architect is to match to the problem and to govern the system with the same rigor you would apply to any mission-critical data infrastructure. So where do you go from here? 3 adjacent domains will define the next frontier of enterprise AI architecture. First, the Model Context Call, MCP, is emerging as the standardization layer for how agents communicate with external tools and data sources. Understanding MCP integration will become as fundamental as understanding API design was a decade ago. Second, LLM-based query routing, the ability to dynamically classify incoming queries and route them to the appropriate RAG tier, model, or tool without human intervention, is the intelligence layer that makes multi-tier RAG systems operationally viable at scale. Third, multi-agent system design, coordinating multiple specialized agents with defined roles, shared memory, and conflict resolution protocols, is the architectural pattern that will underpin the next generation of autonomous enterprise AI. Each of these topics deserves its own deep dive lecture, and each one builds directly on the decision framework you now hold. The architects who master these 3 layers will not just build better RAG systems, they will define what enterprise AI looks like for the next decade. The question is no longer whether RAG is the right architecture. The question is, are you making the right decision at the right tier with the right governance? You now have the framework to answer that question with authority.